Okay, welcome everyone to today's lecture. And where we've come from is we've had a look at the Hammett equation, and we've had a look at how to graph the Hammett equation. So what we have is a reaction of interest, and of course you have to, for a reaction of interest, you have to have different substituents. You have to run the reaction many times and record the rates, and then you have to also do the rate of the unsubstituted case. And so on the y-axis you plot log of kx over kh, and you plot that on the x-axis against the Hammett substituent parameter sigma. And then you get a graph that either has a positive slope or a negative slope, or maybe a very small slope. And we interpret that graph as if you have a positive slope, it means that there are electrons coming towards you in the rate determining step. And what do I mean by towards you? I mean that if you're sitting on that aromatic system where the substituents are changing, if you're sitting on that probe, then electrons are coming towards you. If it's got a negative slope, if you're sitting on that probe, electrons are moving away from you. And of course, there are three cases that we've encountered where the gradient could be very small. And the three cases were if the reaction center is far from that probe. So if the aromatic system is far from the reaction center, then adding electron donating or electron withdrawing groups is not going to affect the reaction very much. So your reaction constant will be very small. Another case could be if the reaction center is close to the aromatic system but involves a loss and a gain of electrons, then there's no net movement of electrons towards or away from you, and so the reaction constant will be small. But there was a third unusual case in which you have an equilibrium that precedes the rate determining step, and I've got it over here. So you'll see over here, in the rate determining step, you can see here's my probe, here's where I change electron donating, electron withdrawing groups, and of course this is the fragment that the probe's on, and it's receiving electrons. So we expect a very, very strong positive slope in the Hammett plot. So changing this surely would be accelerated by electron withdrawing groups, because electron withdrawing groups would enable pulling electrons into that fragment. But we see it's not, because it's preceded by an equilibrium. And in this equilibrium, we have a loss of a pair of electrons to that H+. So the equilibrium involves a loss of electrons from the probe. You're sitting here, the electrons move away from you, even though in the rate determining step, the electrons moving towards you. So the gradient, the Hammett gradient of a Hammett plot is nearly zero. Okay, so the two hydrolyses that I want to look at, ester hydrolyses that I want to look at, are the base catalyzed ester hydrolysis and acid catalyzed ester hydrolysis. Remember that in concentrated acid, we had a third lot of mechanisms available to us. I'm not interested in that so much. I'm interested in dilute acid assisted ester hydrolysis. I'm interested in this case where we noticed that the rho was very, very small. And I'm interested in base catalyzed hydrolysis where we realized that rho was very, very large because of electrons moving towards the probe in the rate determining step. Okay. And I'm interested in these two particular reactions because it's interesting that in the first reaction, it's very sensitive to electron donating and electron withdrawing groups. It's very sensitive to polar effects. And this one is not. This reaction is not. So these two reactions form the basis for the Taft equation. Taft was interested in moving away from this aromatic system. He wanted to move away from the meta and para substituted aromatic systems to aliphatic and maybe ortho substituted aromatic systems. But remember what the problem was in our first lecture. The problem with those is that there's a steric problem. The moment you have an ortho substituted aromatic system, if you've got an ortho group here, then of course in this tetrahedral intermediate, it clashes with this O- that's formed in the tetrahedral intermediate. So what Taft was interested in was moving towards those problematic cases. So what's interesting is that if we move to those problematic cases and we introduce the steric problem here, let's match it on this side and introduce the same steric problem here. What's interesting is that then the reaction you'll see here is not only that 2.55, but you'll see it plus steric. And this reaction here will not only be naught, but it will be naught plus the steric. So what you can do then is you can use these two reactions together to get rid of the steric component. So if you introduce a steric problem in this reaction and a steric problem in this reaction and use them together and subtract this one from this one, you're going to only be left with the polar side of things. And so that's what Taft did, is he moved away from aromatic systems where there's no steric problems and to aliphatic systems. So you see his base case didn't have an aromatic system here, but had a methyl group here, which is probably the least problematic, but it's still problematic in terms of steric problems. And so the methyl case, the base case, is a methyl case here and a methyl case here. So that is the reference reaction now, is the acetate ester, the methyl acetate ester. This is the base reaction with a methyl group here. And he generated a whole set of parameters using this form. So the base catalyzed, compare it up here, the base catalyzed reaction. So he used several R groups, and some of them will introduce really bad steric problems. But of course, the base catalyzed includes both polar and steric components. But the acid catalyzed has no polar components. It's only going to be influenced by steric components. So if we subtract doing the reaction in base with the reaction in acid, you can get rid of every steric problem and you'll be left with a polar component. And he defined his polar substituent components as being for a particular R, if you put a particular R group on that, and you compare it to the methyl case, you can get out these Taft substituent constants. And these are the table. This is the table of the polar substituent constants. Of course, we expect that in the acid catalyzed, the only problems are steric. And so there's no polar component to it at all. And so he used log of any R over reference as being his steric component. So if you're going to use a Taft equation, what you're tasked to do is that you need to have a whole lot of reactions. So not ester hydrolysis, you'll pick your own reaction that you're interested in, and you will have a whole lot of R groups. But you must do the reaction with a methyl group. And if you do the reaction with a methyl group, then you've got your own internal reference of a methyl. And on your y-axis, you can plot the log of a rate over the methyl rate as being your unsubstituted case. But now your task is to find a rho and a delta that fits the curve. So if you get a rho and a delta, then you will know exactly how polar substituents affect the reaction, and you will know how the steric parts fit the reaction. So the Taft equation enables you to be able to obtain rho star and delta, which is the susceptibility of your reaction to polar effects and the susceptibility of your reaction to steric effects. So what I'm doing is I'm trying to show you how we can be more involved with linear free energy relationships, and we're not tied to aromatic substituted systems. You might want a more general case. You might want to be able to look at aliphatic systems, in which case you need to take into account steric components to your reaction, and of course the the electron donating, electron withdrawing still affect it, but the Taft equation is your go-to to work with. Okay, right. So that's the first alternative to the Hammett equation that I want you to be aware of. So the Taft equation is not just about electron donating, electron withdrawing. It's also about taking into account steric effects in a reaction. And of course, in the Taft equation, the reference is not aromatic at all. There's no aromatic in this list at all. The reference is simply the methyl substituted system. Right, that's the first. But of course, now have a look at this. You should recognize this reaction that we've got here, because this is the standard for our Hammett substituent constants. This is benzoic acid, and these are the acid dissociation of benzoic acids. And remember, to get our sigma values, you have to do log of the equilibrium Kx over equilibrium Kh, and that gives our sigma values that are fill all the tables that we use. This is the reference. This is the standard for our x-axis. This is how we obtain our sigma values, our Hammett substituent parameters. But what's interesting about this reference reaction, the standard, is that if we plot it against itself, so if we plot log kx over log kh against log kx over log kh against sigma against itself, of course we get a gradient of 1. That's by definition, of course, because that's our standard. But of course, if we change the solvent, and plot it against with water, so if we change the solvent to 80% ethanol, 20% water, you can see that the reaction constant changes. And if you work in pure ethanol, the reaction constant is different again. That's really interesting. It's really interesting that changing the solvent of a reaction changes the effect. It has a huge effect on the reaction itself. So changing of solvent is really important, and many researchers have recognized this. And so the first people to deal with solvent effects was Grunwald and Winstein, and the Grunwald-Winstein equation first was interested in getting some parameters for solvents. So what they did was they decided on a reference, their own reference reaction, and here's the reference reaction they used with tertiary butyl chloride. And of course, you've got SN1 formation of a tertiary carbocation. And this is not sulfur, this is solvent SO minus. And SO minus then comes in and it comes into the positive charge as a nucleophile. So what happens is they've measured this rate in different solvents. So the reference reaction, you do it in a solvent, and you do it in the reference solvent, and you get your solvent parameters for it. So what's the reference solvent? The reference solvent is 80% ethanol in water. So Y is defined to be 0 for 80% ethanol, 20% water. And so what they've done is they've done this reaction in many different solvent combinations. So you can see they've done it in pure ethanol, pure methanol, in various mixtures of ethanol and water, and these are the YAs that you get for that. So these YAs we can now use to explore solvent effects in reactions. And what we've got to do is we've got to do a whole series. We've got our reaction that we're interested in. We've got to do that reaction many, many times in many different solvents. So you're not changing substituents now. It's exactly the same reaction. You only have one reaction that you're interested in, but you do that in different solvents. So your graph is not about changing substituent, it's about changing solvent. Okay, so you have to get the rate of your reaction in many solvents. This is one reaction in different solvents, including the reference solvent. And then your y-axis is a log of a ratio of a reaction in an arbitrary solvent over a reaction in a reference solvent. And what's interesting is that when you're trying to explore SN1, SN2 reactions, for example, the gradient can tell you whether it's SN1 or SN2. And so if your gradient, if you plot log K over K naught against YA, if your gradient is greater than or equal to 1, you can be assured that your mechanism is an SN1 mechanism. So that because SN1 will be affected by solvents in that way. Okay. So that is one way that people are able to deal with solvent effects and to explore how solvents affect reactions. And of course, the upside of it is that we know a lot about SN1 and SN2 reactions and how they're affected by polar solvents. And so we can use that to determine whether the reaction mechanism is SN1 or SN2. Okay. But of course, other researchers have other ways of working. Other people have used other ways of working with solvents. And so I want to just give you another way that people have looked at solvents. And it's a really interesting dye. And so this is Dimroth and Reichart. They generated this dye over here. This is a really interesting molecule because you take this molecule, you dissolve in water, and that's what it looks like. If you take that same system, that same compound, dissolve in methanol, you get different colors depending on which solvent you have. So that's really fantastic. You've got really different colors coming out from one dye depending on the polarity of the solvent. And so they use that color to create a scale. And so what you need to do is you need to run your UV-Vis spectra of all of these and search for the maximum absorbance in the UV-Vis spectra. And from the maximum absorbance of all of these, you can get these ET30 values that can be used. And these are a table of reference values. And here's your reference values over here. And so these are your X values that you're going to use when you study your own reaction, how your own reaction is affected by solvent. So for example, in the solvolysis, that means the breakdown of that molecule in solvent, in the solvolysis of this particular molecule. If you plot ln of k against these values, you can see that you get a slope, a positive slope. And of course, the value of the slope, again, relates then to whether it's an SN1 mechanism, so the loss of the tosylate group in that, and in the study, the particular study where they explored this compound, they were able to determine that there was an SN1 mechanism, so loss of that group to form a carbocation in some manner, and that is confirmed from that. So what I'm trying to say here is that reactions are not just about electron donating and electron withdrawing. It's not just about a Hammett plot and getting a positive or negative slope. Reactions are more complicated than simply electron donating and electron withdrawing. Of course, in general reactions, you might not have an aromatic system. You might not be able to do the meta and para substitute aromatics. And in that case, you have steric factors. So not only do you have electron donating, electron withdrawing, you've got steric factors. Don't forget that you've also got solvent effects. So please, reactions are more complicated than simply electron donating and electron withdrawing. Okay. So what we've done in this course is we've explored the Hammett plot and the Hammett equation. And then, of course, when you plot it and you get a gradient, the gradient can be positive, indicating a movement of electrons towards you in the rate determining step, or negative, meaning movement of electrons away from you in the rate determining step. It can be large or it can be small. And we know there are three reasons why we can have a small reaction constant. Of course, I've come across two cases and I've given you two examples of concave up and concave down plot. A concave up plot means that there's a choice of mechanism. When you have a choice of mechanism, the fastest mechanism is going to give you your products. Of course, if you've only got one mechanism available to you, there may be several possible rate determining steps. And of course, it's the slow step that is rate determining. And of course, a concave down plot means that there's a change in rate determining step as you move from electron donating groups to electron withdrawing groups. And finally, reactions are not just about electron donating or electron withdrawing. Other factors are important in reactions. We mustn't lose sight of them, such as solvent or steric factors. Okay. And that brings us to the end of quite a long session, and I'd like to thank you for your participation in the course. There's a sector of the class that has not been able to participate, and I'm hoping that when we are finally back, we'll be able to engage and get them up to speed with you. But please, can I encourage you, please, I still need to mark a lot of the tasks on Are You Connected? Please be patient. I will try and get to that as soon as I can. And I will need a mark from this section of the course. So please engage with the tutorial, because at some point in the future, I'm going to need a mark from Hammett, from linear free energy relationships. Further, please don't forget that there are practicals available. And if you've got any problems with the pracs, you can contact me. Or if you want to set aside some time for a small group of you to run through either the scripting prac that I've made available or for the molecular modeling prac, I'm willing to do that. But please just liaise, get a group together, make a time, and we can meet on Zoom where we can perhaps share screens so I can see what you're doing on your end, and I can show you what I'm doing on my end as well. Okay. But as always, at any point, if you have any questions, any queries, I'm free to be contacted, certainly by email. And if you need, as a group, to Zoom, I can set up a Zoom meeting for you to deal with whatever problems you're dealing with. Are there any questions? I don't have a chat open on my system. I just want to check if there are any questions on the chat. No? Okay. So that's it from me for now. So look out for Prof. Mac tomorrow. I'm not sure what he has available for you. But of course, if you have any questions at all, please will you contact me and I can sort that out. Okay.